Hello, so here's another video on blockchain basics. After having discussed the blockchain data structure and how the ledger is cryptographically linked and works, I think it's now time to talk about consensus, so how we actually agree on the correct version of the ledger. So yeah, let's get started. So if you remember this slide from the last video, basically to keep the ledger in sync on all the nodes, to keep the blockchain in consistent state, blocks need to be added in a certain way, and the whole system has to agree on these blocks. And in general, consensus is a really misunderstood problem, and it's generally very badly described in blockchain technology. So there's a lot of misinformation out there. So that's why this video will be slightly longer than others, because I think it's difficult to break this down into smaller parts. But anyway, to maintain the ledger in sync, as we said last time, there are two steps basically. So you need to choose a block producer and to reach consensus on the block's inclusion between all the other nodes afterwards. So basically these two blocks correspond to, in Bitcoin, that would be proof of work for choosing the block producer and then the consensus afterwards. So if we look at the block producer selection, that's typically associated with mining. There's different types of mining gear. You know, we first started mining on CPUs, then we moved to GPUs, and now we have very complex setups with special purpose hardware. But there are alternatives to selecting the block producer, not just mining. But anyway, Bitcoin mining was the original way of doing this. And we sort of start the discussion by using this. What is important to notice, though, is that proof of work is not a consensus algorithm. It's just a way of producing the block producer. So yeah, proof of work, Bitcoin mining, or whatever you want to call it. Ethereum uses a very similar algorithm. This is a traditional blockchain mechanism for selecting the next block producer. And this is how it works in Bitcoin here. This diagram just shows how the hash of the previous block header is calculated. So what happens is the miners are collecting transactions from the pool of unconfirmed transactions, and they're building their blocks. And they are closing these blocks off by calculating the hash of the block, of the previous block. And there's a difficulty target for this. Basically, it should be below a certain number, or it should be starting with a certain number of zeros, which is essentially the same thing. Basically, they are calculating in Bitcoin the SHA-256 hash, and the difficult target is calculated so that on average should take about 10 minutes in the network. And it's basically a race of time against time, right? So there's a race between the different block producers or miners. So they just announce, which is a number used only once in the block header, and they use that to calculate the hash. And obviously that hash will most of the time not fit the difficulty target, but basically by adjusting this number randomly or by whatever algorithm they see fit, they can essentially eventually find a version that fits the target. Because basically what this announce does, it changes the hash. So if you only change this announce slightly, the hash will change completely in a completely unpredictable way. And anyway, when a hash is found, that miner that finds this hash basically wins. So it's like a lottery. And of course, two miners can, or several miners can find a hash more or less at the same time. But that doesn't matter. That's what consensus is for. Whenever a miner thinks he's the first to have the solution, he closes off this block and publishes to the blockchain. And then we enter the next phase, which is consensus, which comes after proof of work. So just to see the purpose of proof of work, basically it acts as a giant number generator, a giant random number generator. So it's a lottery, right? But computational power is used to influence the probability. So the randomness is weighted by the computational power. The more computational power I have, the more likely I am to find the next block. But there's still a random element to it. And basically, we have to do proof of work. Or originally, we did proof of work to make it very expensive for people to obtain multiple lottery tickets in this lottery. And that's something called cyber attack resistance. But basically, it makes it very hard to have an infinite or very large number of participations in this lottery. So it makes it fair in a way and more random. However, proof of work is of course associated with some problems, and basically it wastes a lot of computing power, which has some environmental impact, energy consumption and such. And a problem related to that is it favors mining in places where electricity is cheap, which is why at some point we had very strong Chinese mining cartels, because they could mine more profitably than people in other places, and that's obviously not good. So those alternatives, and proof of stake was one of the first to emerge really, and the initial protocols using proof of stake were very primitive but have now become much more sophisticated, and Ethereum is switching to proof of stake in the version 2.0 of their protocol. But basically the observation is, if more computing power is related to being more wealthy, if you have more money you can buy more computing power, then why not just use wealth directly as a weight for choosing the block producer? This random lottery, why don't we weight it with a stake in the system? You have to hold a certain number of cryptocurrency to be able to participate in this. And so participants just stake their funds, and they can lose the funds if they misbehave, but basically they lock them up, and the more I have locked up, the more likely I am to be chosen as the next block producer. So that's of course much more energy efficient, and it's better for the environment and less wasteful, and should in theory be a better protocol, but it's difficult to get it to work correctly, and one of the reasons is that we are missing the randomness of proof of work, because the entropy of a lot of people trying to find solutions and changing announs and producing different hashes is lost. So there's a missing entropy for randomness, and it's very difficult to get true randomness weighted by the stake in proof of stake. And there's a lot of ongoing research on this. And then there's delegated proof of stake, which is basically it's an optimization of proof of stake in where you can actually, where people or nodes delegate their stake in the system to a number of validators, and usually that's fixed to 100, 1,000, or even as low as 21 in some systems. But the advantage of this is you then have a small set of validators which take turns or have some mechanism to take turns in producing the blocks. And knowing who these validators are and having a fixed number of them is very useful to optimize consensus, which is the next step in the process, which we'll talk about in a bit. So this is really modeled on the way democracy works. So you elect leaders that vote on your behalf or act on your behalf. And anyone can be a candidate really, but the votes are also based on wealth, so it's not a truly democratic system in that every vote counts the same. But anyway, it can be very efficient, and is one of the ways blockchains can scale. So when it comes to consensus, there are several ways of doing this. So we basically we have decided who the next block producer is. And occasionally there might be two block producers at the same time in proof of work or very close together. But anyway, for every block, the nodes have to come to an agreement on whether to include the block or not. And in the case of forking, which is the process of two blocks being valid at the same time, or being produced at the same time, they have to decide which path in the chain to take. And basically, the Bitcoin's consensus algorithm is extremely simple. We just call it Nakamoto consensus, but could be called anything really. Basically, it just means the longest chain wins, or the chain with the biggest support in terms of computing power wins. So once we get a bit of a fork in the chain, like in the example here at the bottom, it's just a race against which of the chains have more adoption, and the other one will eventually die out because miners obviously switch to the one they deem more correct, because that's where they get their mining report from. So really this Nakamoto consensus just is the longest chain wins. There's nothing particular about it. Now this has of course the effect that on this upper chain here, this fourth block, or block 4 here, might actually be disregarded. Well, the whole chain, the whole side chain will be disregarded, but it actually means that transaction can occasionally be undone. And it's probabilistic in a way. We'll talk about this in a second. But just to compare the original BFT consensus, which stands for Byzantine fault tolerance, that's protocol. That's a protocol. Well, a way of describing the problem from an algorithm from the 1980s. And there was an efficient implementation called Practical Byzantine Fault Tolerance in '99, way before Bitcoin or blockchain. But it's a consensus algorithm, and it's often used in blockchain. It's particularly useful in situations where you have a fixed number of nodes or validators. Basically, without going into much details, the participants vote and send a number of messages approving blocks. And this, of course, scales poorly in the sense that the more validators I have, the harder it gets for all of them to vote and commit to their opinion. And that's why we really use it quite often in situations where there are consortium chains, where we have a small fixed set number of approved validators, or in something like delegated proof of stake, where we can actually reduce the validator set to something manageable. So just to compare the two, which are extremes in a way, that they're different intermediate algorithms. But in Nakamoto consensus, we don't really have a consensus as such. We just sort of have the longest chain win. So if we think about when a block becomes final or a transaction cannot be undone anymore, in Nakamoto consensus, which we use in Bitcoin, the answer is theoretically never, because it's probabilistic, right? The probability that a block will not be undone increases with every block added, but it's never zero, mathematically speaking. So this means we have to have a delay before we can assume a block is final, will not be, a transaction not being undone. And in Bitcoin, that's usually considered to be an hour as a safe delay. And this is really why when we do make a big transaction, we are asked to wait a little bit before we confirm this, even if the transaction has been confirmed. And it also means Nakamoto consensus, in order to attack it and rewrite history, you need more than 50% of computing power to attack it. And in general, this is designed to favor availability. because it means you always sort of continue, even if just a couple of nodes are isolated. They can keep accepting transactions and write to their blockchain. They just have the risk of later being undone. And in BFT voting, a block can be considered final once we have gone through this round of voting, which means that more than 2/3 of the validators have approved the transaction, the block, and then it's included. And this means in that moment we have instant finality, and in good network conditions this works really well. That's one of the reasons we use it in smaller validator sets, because if you have 100 nodes which are well connected, it's fairly easy to get to the 67 votes required, and then we have finality almost instantly, and the transaction in this block won't be undone anymore. But the problem is the network will stop otherwise, right? If we cannot reach 2/3 of the nodes, or they refuse to vote, or whatever is happening, the network cannot continue. Whereas in Nakamoto consensus, they just keep adding to their minority chain and hope for the best. Which means that BFT voting really does not favor availability at all, but it favors consistency. Once a block is confirmed, it stays that way. And this is a difference in philosophy, which, it's always a trade-off. You can either do availability or consistency in situations where a network might partition or nodes disappear and come back. And that's called the CAP theorem. You cannot have partition tolerance, availability, and consistency at the same time. So in the presence of partitions, you have to choose between availability or consistency. And of course, for different applications, there might be a different preference. So BFT voting might work really well for some applications, but Nakamoto consensus might work really well for others. For example, completely open peer-to-peer cash systems like Bitcoin, where you really don't want to limit your set of validators and anyone can participate in the system. So anyway, that's what I wanted to discuss on consensus. It's really very misunderstood. The important takeaway from this video here is that it's a two-step process. You first have a way of selecting the block producer, and then you have an actual consensus protocol. So proof of work, for example, is not a consensus protocol. It is sort of a giant lottery which acts as a block producer selection mechanism. Anyway, that's all for now. I'll be back soon with another video.